Welcome to section 1.6, Power, Polynomial, and Rational Functions. I'm going to split this section into 3 videos. One will be for power, one for polynomials, and the other one rational functions. In this section, we're going to make sure that you're familiar with the behaviors and properties of power, polynomial, and rational functions. This course does many functions of these types and many of its sections and applications, so it's important we review them. Okay, you will be able to identify the different graphs and features of power functions, which is y equals kx to the p. Compare and contrast exponential, power, and linear functions. Identify the degree and maximum terms of polynomials. Determine the end behavior of polynomials of even and odd degrees. Determine a polynomial with given zeros and a point. And find vertical and horizontal asymptotes for rational functions. Okay, let's start with power functions first. What do power functions look like? Excuse me. A power function is a function in which the dependent variable is proportional to a power of the independent variable. So power functions are written in the form of f of x equals kx to the p, where k and p are constant. So here it is, y equals kx to the p. Excuse me. So the p is up high. P is your power, your exponent in this case. Okay? Now, let's compare versus what you're used to with exponential, the y equals ab to the x, where you see that a and b are your constants and this is your variable. Here, your k and your p are constants, and the power is your exponent, if you will. So these are constants here. Now, the best way to say this is the x is up high if it's exponential. If it's power, your variable or your x is down low, if you'll see. So it's y equals kx to the p. We will only look at whole numbers, 0, 1, 2, etc. here. So here's some examples of power functions. You have f of x equals 2x cubed. Notice this is a constant and this is a constant. G of x equals 5x to the negative 2, and h of x equals 7x to the half. So see where the x is down low, and I wanted to give you some examples. Many students find it easy to confuse power functions and exponential functions. Both have a format that is given by 2 parameters. Both formats look very similar. To tell the difference, look where the independent or input variable is located. In exponential functions, a fixed base is raised to a variable exponent. So here, like I said before, the x is up high and it's a variable, meaning you have to solve for it, and it stays a variable. In power functions, however, the variable base is raised to a fixed exponent. So here your x is down low. That's just to help you so you can see the difference quickly, okay? So if we look at the next page, exponential functions, y equals ab to the x. Power functions, y equals kx to the p. Here's an exponential function, 3 times 0.5 to the x. See how the x is variable? Here it's 3x to the 5th. The variable is down low. Y equals 100 e to the negative 2.2t. Notice the variable is up high. Y equals 6x to the negative 2. See how the variable is down low. We will only be looking at whole number exponents. We will first look at odd and even powers, and then the special case when the power is 0. Odd integer powers. Odd power functions are functions in the form of x to the p, where p is odd. So here's an example. I graphed first y equals x, y equals x cubed, y equals x to the 5th. So this has a power of 1, 3, 5. See how they're all odd. And if you'll notice on here, the characteristics of this is it's a straight line when it's y equals x. Do you see it right here? And then as soon as I do y equals x cubed, it starts bending. X to the 5th, it's bending, but it's even narrower. X to the 7th would look even similar. It kind of come down like this. And the higher the power, the steeper it gets, your curve gets. And I call for characteristics of this, I think it looks seat-shaped. Characteristics. It reminds me of those plastic seats that you get. So I call these seat-shaped. With the exception of y equals x, they all look like that plastic seat I was telling you about, those molded seats you can use. Okay? Let's look at some of the things we need to know about them. We often hear the shape of odd power functions with a power greater than 1 as seat-shaped. Okay? This is because some people think odd power functions greater than 1 look like a human sitting. All odd power functions share 3 common points. They have negative 1, 1, negative 1, negative 1, 0, 0, and 1, 1. When examining odd power functions, we notice they change concavity. So see here how this part right here is concave down, like a frown. And let me go up a little. This is concave up, like a cup. See, so it changed concavity as it was going. All graphs of odd power functions are concave up for x is greater than 0 and concave down for x is less than 0. We will also look briefly at when we refer to the end behavior. By the term end behavior, we mean the behavior of the y values when the x values are allowed to go either positive or negative infinity. So let me explain to you on this how we describe it. We use x as a direction. So here, when I go to this direction, we're going to positive infinity. For x here, it's negative infinity. Down here for y, this is negative infinity. And for y up here, this is positive infinity. So a lot of times as mathematicians, we'll ask you for the end behavior. What I mean by that is what's happening to the end of your graph as we go to positive infinity for your x, or the left is negative infinity. So let's look how that works. So here we can say as x approaches, and that's what that arrow means, x approaches positive infinity. So we're going to the right. What's happening to my y? Well, my y is also approaching infinity, meaning it's getting higher. So let's look up here. As x approaches infinity, see how my y's are going to infinity? So we're describing it, and remember, math people like to have symbols, so that this arrow means approaching. The direction you're going, okay? Again, as x approaches to negative infinity as we go to the left, our y is approaching negative infinity also. Okay? That's how we say that. The next, even integer powers. So if our powers have even numbers like y equals x squared, x to the fourth, x to the sixth, keep going, you'll notice this is our main parabola. They look U-shaped, if you will. Okay, so this characteristic here is they look U-shaped. Okay, now we're used to parabolas, but look what x to the fourth looks like and x to the sixth. They look very similar, except they're getting narrower and narrower as the power gets higher and higher. So we call the shape of power functions that are even as U-shaped, like I told you above. All odd power functions, all even power functions share this should be even, sorry. Power functions share 3 common points, negative 1, 1, 0, 0, and positive 1, 1. Okay? The next thing is even power functions are everywhere concave up. And if you can see this is concave up on our picture. And the end behavior, they've kind of written it this way, but as x approaches positive infinity, my y is approaching positive infinity, and as my x's approach negative infinity, my y's are also approaching positive infinity. So it's going up in both cases. The zero power function, this one's a special case. Zero power function, if it's x to the 0, it says recall that any non-zero number raised to the power of 0 is equal to 1. So this is equal to 1. So you can say y equals x to 0 equals 1, except for x is equal to 0. So there's really a hole in our graph right here. This is really the graph y equals 1. But 0 to the 0 is undefined, so there really is a hole there. You'd have to really go very closely to see that, but it's a straight line of y equals 1 except for that hole at 0, 1. Okay? Now because you learn better by comparing, let's compare exponential and power functions. When we refer to dominance, we mean which function is in control or more powerful as x approaches positive infinity. For our purposes, we will we will look at the special situation in which one function will become much larger than the other as x gets very large. So basically we're looking at what function wins the race, if you will, in the long run. So we're looking at which function is getting large quicker, okay? The function with the larger power will always dominate as x gets large. So for example, here they have y equals 12x cubed, I graphed that, and y equals x to the fourth. Now if you were to really zoom this out, I mean this is quite a large window, you'll notice that y equals x to the fourth looks like it's not winning. See how? And then all of a sudden it takes over, and see how it's closer to the y-axis? That means my y values are getting larger quicker. This one says to dominate. It dominates the other power. Okay? For x values greater than 0 but less than 12, the function is larger. For x is larger than 12, the function x to the fourth is always larger. So you can say that if it's power versus power, right, so we're going to talk about this. If I have two power functions and I want to see which one dominates, okay, the larger power always dominates. It doesn't matter what the coefficient in front, it always dominates. Okay? Now we have another one. If we compare exponential functions, this is important. Exponential functions dominate over power function when x gets large, always. And how you can remember that is e comes before p in the alphabet. So exponential functions always dominate power functions. Okay, so let's look at this on the next page. So if you'll see, if I had y equals x cubed, so here I have y equals x cubed. This is a power function because your x is down low. I have y equals 2 to the x. This is exponential. And you can graph it and check it, and I always have people say, oh, you're wrong, but you have to make your window very large. You'll notice that your exponential function, which is here, this is power right here, and here's exponential, will win in the long run. Okay? Exponential always wins. So this always dominates. I sometimes have students that will kind of contradict me, and they'll spend all day during class trying to compare and see, and you sometimes have to make your window quite large to see that the exponential will always win, dominates. And so the window above here shows that it's losing the battle here, but as I get bigger and bigger and make my window bigger and bigger, you'll see that the exponential function here is dominating. Okay, so let's try a couple examples. We'll do it right here at the bottom of the page. So here's my first example. All right, so I have this function y equals 0.005 1.04 to the x, and then I have y equals 1,000,000 x to the 1,000. It's a 0, guys. Okay. And if I asked you which one dominates, this one right here is exponential. This one's a power function. It doesn't matter that the million is there and I'm raising it to 1,000. This dominates because it's exponential in the long run. And then you'd have to really play with the window to see that, but it would work. This is number 2. If I had y equals 0.002 x to the 1/2 versus y equals 1,000 x to the -2. These are both power functions. This one's a power function. This one's a power function. And the higher power dominates no matter what. So this one will dominate just because 1/2 is bigger than -2. Well, that concludes our introduction of power functions.